Hello guys! In this video we are going to continue with derivatives. Which are the objectives of this video? We are going to see higher order derivatives, the definition, we are going to calculate some derivatives and apply these ideas in examples. At least we are going to find the derivative of the logarithm in this video. Requirements are as usual, not so high, just something about calculus, we need to simplify, work with powers and mathematical ideas, some mathematical topics that are not very difficult. And I will try to explain during the video all the things we are going to use. Okay, let's see. First, we know more or less what is the derivative. Remember that the derivative of a function at a given point is giving you the slope of the tangent line. Okay, and once you calculate, if the function is differentiable, if we can calculate the derivative at any point, we are like building a new function called the derivative that gives you the slope at any given point. For example, let's put an easy example. Suppose that you have x squared. The easiest function I can think about right now. The derivative of x squared is 2 times x. Okay, so the derivative of a function is another function. And once you forget where this function is coming, let's suppose that I started my talk saying, consider the function 2 times x. It's a very easy function. It's a polynomial. It's nothing. Then we can calculate the derivative of this function. But be careful, the derivative of 2x is the derivative of the derivative of x squared, okay? So, the idea is, if we can find the derivative function, we can keep going calculating the derivative of this function. This is what we call the higher order derivatives, okay? The second derivative, the third derivative. They are normally denoted like you see on the screen. We put the order of the derivative between parentheses and with a Roman numeral notation. Okay, could be the first one, the second derivative, the third derivative, the fourth derivative, the fifth derivative, and the notation is as you can see here. Okay, what is the n plus 1 derivative? Is the derivative of the nth derivative. Okay, so piece of cake. The idea is that we can keep going, calculating derivatives and derivatives. Let's see an example. The one I was mentioned at the beginning of the video. Consider the function x squared. The derivative of x squared is 2 times x. The derivative of the derivative, I mean the second derivative, is 2, because you know that the derivative of 2 times x is 2. Okay? Can we calculate the derivative again? Yes, of course. Can we calculate the third derivative? The definition of the derivative is here. Okay? It was the limit of the function at the point you are trying to calculate the derivative plus h minus the function at the point you are given, divided by h. But this is the definition. The only thing I just changed in this example is that since I'm calculating the third derivative, the function I'm using here is the second derivative function. But this function is written here. The second derivative is 2 all the time. So what is the value of the second derivative of a plus h? At any point, the function is constant, so the value is 2. What is the second derivative at the point a? I don't even know. I don't even care what is the value of a, because the function is 2 all the time. So I just write here 2. So what is this limit? This limit is 0 over h. And okay, let's just stop here 1 second. Normally you have, my students normally answer me that this is 0 over 0. And that's true, okay? When h tends to 0, 0 over 0 is an indetermination, so we don't know what is the value of the limit. But when this happens, when you replace or when you substitute h by the value you are tending to, like in this case 0, then you should first simplify the function. Okay, I know it's 0 over 0. Do you want to resolve this indetermination? L'Hopital, for example. It doesn't matter. In this case, it can be done. But in this case, it's not necessary. This is too much for a so simple exercise. The idea is that before calculating the limit. Just for imagine that this is not here, and what you need to do is calculate what is 0 over something. And 0 divided by anything is going to, if the denominator is not 0, but in this case, h tends to 0. It's not 0. It's approaching 0. But what is happening here? 0 over something, it's going to be 0 all the time. So first you simplify, then you calculate the limit. And then this way you solve the indetermination that appears in this video. Okay? So in this case, this limit is 0. You don't trust me? L'Hopital, for example. Okay? It can be done. But the key point is that the derivative is 0. In general, the derivative of any constant is going to be 0. And this, you can keep this information as a rule for the future. Okay? So the derivative of any constant is going to be 0. Okay, also the derivative, as a rule, it has been proved here, the derivative of x squared was 2 times x. And the derivative of x, the 2 times x, it was 2. The 2 is a constant. In general, you can say that the derivative of x is 1. And you have this written in here. Okay, let's review some of the derivatives. Probably these derivatives is something you have seen before. Okay, there is a list of derivatives. In order to save time, I don't want to be calculating limits again and again in order to calculate a derivative. I prefer to have a list of functions and apply these derivatives as fast as possible when I'm solving a problem. And here on the screen, what you have is a list of functions and their derivatives. The key point is that if r is a real number, it's fixed, then the derivative of any constant is 0. The derivative of x is 1. Power rule, it's very important. The derivative of x power something is that function. The exponent goes down and multiplies the x, and I subtract 1 to the exponent. Okay, so for example, x cubed, the derivative of x cubed is 3 times x squared. The 3 goes down, and to the exponent I subtract 1. The derivative of x to the 5th power, x power 5, it's 5 times x to the 4th power. Okay, so it's not difficult. It's just a rule, a very common, a very known rule that we are going to apply many times in the exercises. Okay, one more. The exponential function, e to the x. The derivative of e to the x is exactly the same function, e to the x. The derivative of the logarithm, 1 over x. The derivative of sine, cosine. The derivative of cosine, negative sine. So there is even in the textbooks or in internet, you can find a long list of derivatives. These are the simplest list of derivatives because we can add something called the chain rule in order to calculate derivatives of functions that are inside the others. Okay? Okay, let's continue. Why not to check at least one of these derivatives that we have seen before? Let's suppose that you have the natural logarithm. Okay, in order to solve this derivative, we need something first. And I think it's a very nice information. If you knew it before, perfect, because this is not so common. If you didn't know, then let me introduce this equation, this equality. E to the r, the exponential function power r, is the limit when t tends to infinity of this function, 1 plus r over t power t. Okay? To prove this is a little bit more complicated, but this is a formula that we are going to apply. The exponential function power r can be calculated as this limit. Therefore, let's calculate the derivative of the logarithm. The derivative of the logarithm is if we use the definition, this is the definition, and we apply the function at a plus h is the logarithm of a plus h. The function at a is the logarithm at a. What are we doing here? We are in the next step. We just write 1 over h apart, as you can see, and you need to remember that the subtraction of logarithms is the logarithm of the quotient. So when I have logarithm of something minus logarithm of another thing, then this is the logarithm of the first one on the numerator and this one on the denominator. Another property of logarithms, I have a number, an expression multiplying the logarithm. This number or this expression can be written as an exponent, as you see here. Okay? So perfect. I have the limit when h tends to 0 of the logarithm of this expression. Oh, by the way, apart from moving this number to the exponent, we divided the numerator and denominator by a, so it's simplifying this way. Okay, next part. We apply a change of variables. T is going to be a divided by h. So the previous limit can be written like this. And now what I'm going to do is 1 over a that is in the exponent, I'm going to move it here, okay? It's going down, but it's a constant. It can be written outside of the limit. And then, what is this limit, guys? This limit is number e. And also, I can just move the limit inside because the natural logarithm is a continuous function. So the limit can be entered the logarithm, as I did here. And this is number e. And you know that the logarithm of number e is 1. So the final derivative is just 1 over a. What have we seen? We just practiced with derivative. We have seen a list of derivatives that for sure we need in these videos, in any mathematics 1 subject, you are going to need derivatives. And the sooner you remember all derivatives in the list, the better, because it's going to make things easier. And we have seen the proof of why the derivative of the logarithm of x is 1 over x, as we just saw. I hope this is helpful for you guys, and thank you for your attention.